Hey there, everyone. My name is Jeremy McWhorter, and this is my Physics 2211 Lab 4 Oscillations. All right, so intro. This is the goal of this lab was to create a model of an object attached to an oscillating spring, and then use GlowScript to model that, as well as Tracker to physically track the video that the professor gave us. So in the GlowScript, we needed to calculate the changes in energy using iteration, and then compare the computational model that we made in GlowScript with the Tracker motion tracking software with the actual video. In this case, the system would be the earth, the spring, and the ball. And then the things that we were given are the ball mass and the stretched length of the spring, which is L. So the fundamental principles that we'll be using in this lab and in the GlowScript are the energy principle, which is energy is equal to kinetic energy plus gravitational energy plus spring energy. Here, this is just defining what kinetic energy is, which is 1/2 mv squared, and then what the spring potential is, which is 1/2 kx squared, and then gravitational, which is mgh. And then here you can see in the GlowScript where we define k, ug, us, and then the total energy. Moving on. So this is the tracker. Here you can see the different points that it's tracking, and as you can see, the x and y coordinates follow a sinusoidal curve going on the graph, up and down, up and down. And that's just the spring going in motion. I couldn't find a way to put the video on here, but the two screenshots show the tracker of the ball at the bottom and at the top of the curves. So that's the actual tracker physical software. And then here are the calculations we did for the spring in the GlowScript. First off, we had to define what our spring constant was, which is, through calculation, found as 6.83. Newtons per meter. And then here you have to set the force of gravity equal to the force of the spring. So that means mg is equal to the kinetic energy, or the force of the spring. So here you can find that eventually, using the difference in the spring law, you find that the period is equal to 1.519 seconds. Using the spring constant relation to period, as shown in the equation above. All right, so here is the actual GlowScript that we use. So this is the computational model. Up above, as shown before, we defined all our different energy principles up top. So kinetic energy, gravitational energy, spring energy, and then the total energy principle. And then we set our iteration while t is less than 5.8 seconds, because that's what we defined as our period. We iterated finding the force of gravity, spring, and then the F-net. And then we related that with the spring formula. L is equal to L hat and mg. And then moving on over here, we defined what gravity was, and then the force of the spring, and then the displacement of the spring. Here overall, we just iterated finding the different positions of the ball on the spring as it was oscillating throughout the space. All right, and then here is what we found from the GlowScript. These are the two graphs. So this is comparing the x and the y. So as you can see, it followed the same kind of sinusoidal form as the tracker software did. So this is just a computational model of what we expected the value to be versus what it actually was. And then lastly, what does this mean? So the first question was, is the energy principle satisfied? And as you can see in this graph, the yellow line is delta E, which is the change in energy. And as you can see, that is pretty close to straight zero. And because change in energy is equal to zero, that means the energy principle is satisfied. So, and then the other one is we had to calculate the different periods at the different points of oscillation. So as you can see, when we selected a data point at the top of the oscillation, we found the period of oscillation to be 1.65, and then we found one at the bottom of the oscillation, we found it to be 1.52. So it depends on what point you select in the tracker, but you can compute different periods of oscillation.